Our next speaker is one of those guys that makes your life a lot easier if you work at a big company. He works on infrastructure teams. They help devs integrate their code, and he likes it, right? He likes to optimize continuous integration processes, speed up builds, tests, and even deliver tools that developers use. So please welcome Vlad for remote code signing.
Good afternoon, and thank you. It's a big privilege to speak in Spain, and this audience is awesome, right? Yeah. A little word about me. I work in Bloomberg as a software engineer in the mobile connectivity and tools team. So we maintain the backend for the mobile applications, allowing the apps to fetch data from the microservices. And the other part of our job is to maintain CI/CD systems and pipelines and testing and tooling and developer experience and stuff like that. And today, I'm going to talk to you about how can we secure the code signing on Apple platforms. Essentially, my agenda is we'll dig into what the code signing is, how we traditionally approach the code signing process, how can we make it more secure, and how can we essentially design the tool that will let you perform this signing process remotely on the backend. First, I would like to start with a crash course of code signing is. I'm pretty sure all of you are mature developers, so you know that, but I believe there will be something that everyone can learn from. The code signing is the process of digitally signing the code with a certificate which is issued by the trustworthy authority. For example, Apple or Adobe or Amazon. If we see the code signature, then we can reason about where this executable is coming from, right? We can ensure the origin is valid. Probably we can think of like there is nothing malware inside the executable if it's signed by Apple, for example, right? And it also validates the authenticity. So after we transfer the executable over the public networks, it means like the code didn't change, right? It's still valid. And we also absolutely need the code signing to distribute the apps. Whenever we submit to App Store, whenever we distribute outside of App Store, everything has to be signed. What is code signature? It's very simple. It's essentially hash with a certificate that ensures that the value of hash is valid. So hash ensures integrity and certificate ensures authenticity. You can always dump any, like the code signature from any executable by using code sign -d command. I guess the interesting bits here is like this integrity part, which is the hash, and the authenticity part, which is all the certificates that are embedded into the code signature. Whenever you build any code in Xcode, on CI, or in the app itself, Xcode tends to call code sign command. You may see something like this in the build logs. This indicates that something got signed. How it works is code sign looks up the private key for the signed identity we are using, then it hashes the binary, then it signs the hash and embeds it into binary, embeds the resulting signature into binary using like code sign allocate tool. Essentially all builds that are being built are signed, whether it's local build on CI, something we distribute. Let me briefly describe what the code signing identity is. It's not that every certificate can be used to perform the code signing operation. There should be like a private key and the certificate with the extension, which is called digital signature. So only those certificates can be used to sign the code. And that certificate also has to be trusted to actually perform the code signing operation. And that brings me to the topic of certificate chains. every operating system, macOS, Linux, Windows, is shipped with TrustStore, right? So there is a bunch of certificates, which are root certs, which are coming from respectable establishments like Apple, Amazon, DigiCert. They are trusted by the system by default. And for example, in macOS, you may find them in System Root's TrustStore in the keychain application. However, the certificate that you use to sign is not root, right? It's some leaf certificate, developer certificate, or distribution certificate. How does macOS ensures that that cert is valid? That it can actually be used to not like only launch the executable, but also to sign some code. So intermediate certificate authorities come to help. For example, most of developer certificates issued by Apple are actually issued by this intermediate cert called Worldwide Developer Relations Certification Authority. And whenever you start Xcode, it gets installed to the system by default by Xcode itself. On CI, probably you'll need to kind of add this to TrustStore yourself manually, because usually you don't start Xcode in GUI mode on CI machines. So whenever there's a complete chain from the leaf cert to the trusted root cert, it makes that the leaf cert can be trusted. That's easy. For developer ID, it's a bit different story, because the certification authority for them is trusted by macOS, which means all macOS apps that signed with developer ID certificates are trusted automatically out of the box. And there is like enterprise account on iOS, which lets you to distribute the apps outside of iOS App Store, directly to the devices. And in this scenario, iOS only trusts the root CA, but the whole chain is actually embedded into the code signature. You can explore the whole chain of certificates by running this code sign command. It's essential to obviously protect the sign identities, right? Because you don't want the private keys to be leaked. But what happens if any of the private key actually leaks? It depends, in my opinion, on what level of of that sign identity it is representing. So, for example, if the developer private key is leaked, or even distribution the private key leaked, which you use to App Store to publish to App Store, probably not very big deal, because hacker would need to have access to the account to submit to App Store. I mean, it's bad, but you can just revoke the cert and make sure you change the account password, stuff like that, and you're good to go. However, if developer ID private key is leaked, or some enterprise account private key is leaked, so that's a big deal, right? Because these allows the application to run directly on the devices without any reviewal process. And there could be consequences why this leaked, right? There could be a news scandal that, I don't know, something was signed by a very major company, right? Some malware, like cryptocurrency miner software, was signed by X company. And the account can be terminated or suspended while Apple investigates why that happens. So protect this, please. Let's talk about how we traditionally approach the code signing process. Obviously, every developer has its own sign-in key usually, and you store it in the keychain, which is fine. I think it's clear that we should not store distribution private keys on the laptops, on development laptops, right? So, for example, on CI machines, we actually have to expose them to the machine, because we need to sign the app that is ready to be uploaded to Apple. So we tend to do something like encrypting the private keys, or embedding them into a P12 file, for example, and then decrypting as part of CI jobs, not forgetting to delete them from the keychain after we finish, stuff like that. However, on CI, especially in-house CI, which you can run inside your organization, it's relatively easy to fetch those keys from the keychain, because CI job has access to every credential it needs to create that keychain, to delete that keychain, to import into that keychain, right? So essentially, you can create, for example, some iOS unit tests that will read the environment, extract the credentials, and then run security command to extract the private keys from some keychain. If you just investigate where it lives, you can do that. It's doable. So it's kind of not really secure, apparently. And there could be some random questions from random people in the organization, like coming to you like, hey, I need the private key. I need like to sign some app, super hard to debug, like the code signing doesn't work. Give me, I'll debug it on my laptop, I'll delete it afterwards, like I promise. So it brings some questions, right? Are you sure like the developer machines is not compromised already? How can you trust the person that they don't sign some malicious software with that? If there are multiple people asking for this excuse, then it's very easy to lose track who has got what, who deleted it. Of course, there is no audit whatsoever, what happens, and no easy way to enforce the deletion unless you kind of lock them in the room and delete this private key from the keychain manually, right? It's not very, scalable solution. That brings us to the question of how can we make everything secure? The goal here is we make the private key inaccessible by all means. Maybe even us, the guardians of private keys, shouldn't have access to it. It means we could never share it. We could never deploy it to any laptop, CI machine, and any keychain whatsoever. Just don't let that happen. Also, it means that we should be storing it somewhere we trust. Usually, it means backend. And potentially, we would like to have some audit. What gets signed, when it gets signed, by what private key, what certificate is used, stuff like that. Luckily, there is a way to do that. As you already know, this is default flow when code sign tool gets the private key from the keychain. There is an alternative to that. Private code sign tool can ask some entity to perform the sign-in operation without needing to have the private key. This is called the smart card interface. So the flow is that code sign will still hash the binary, but then it will delegate the code sign operation to some extension, which is called, on my slide, Crypto Token Kit extension, which is the framework that Apple provides for such purposes. And then code sign tool still embeds it back to the executable. And this Crypto Token Kit framework is very nice. It lets you create this safe sign-in flow without actually altering any build process. So Xcode would still see these remotely available certificates as if they are on the local machine. And all the tooling that you expect to work, like code sign tool, product tool, will just work as well. And the API is nice and modern, Swift and Objective-C, whatever you want. This is the example of how it looks like from Xcode point of view. Everything in red is available on the backend and not locally. And local keychain only has access to the private key of the developer account. You start by creating macOS app for that. There is an app for that, obviously. And you add the target in Xcode, which is called Smart Card Token Extension. The flow is that when you start the application, macOS application, it will register smart card with the promises that it has access to such and such and such certificates. And then when Xcode wants to sign something, code sign tool won't find this private key in the keychain. And then it will look elsewhere and it will find the smart card with that signed identity. Yeah, I'll go for that. And the smart card API will actually trigger the extension to perform the code signing process. And then the extension in turn will delegate the thing to backend. And the backend in turn is secure and runs Linux and has Python and stuff like that. And it has access to all the private keys. Let's have a look how we can redesign this application. There will be 3 parts inside this application, like inside this flow, sorry. The application, which uses crypto token key to register promises. Then the extension, which will be asked to perform the code signing. And obviously, the person in backend who actually smokes the cigarettes and performs the dirty job, right? Who actually signs the bytes. This is how the app would look like. Default layout, just executable of the app and the extension in plugins folder. Nothing interesting. Let's concentrate on the crypto token kit application, what it has to do. Obviously, it will fetch certificates from the backend and then expose them through smart card interface. And smart card interface is rather simple. There are only 3 entities you have to know about. First is token driver configuration. You can think of it as an extension of the app itself. So it represents the extension from that application. Then you create models that you feed into that extension, right? You create promises, 1 promise for certificate, 1 promise for the key. And then you store these promises inside extensions persistent storage. So token configuration can be thought of as it's a persistent storage. And it's good because it's actually persistent storage. Like when app quits, those are persisted. When system reboots, the smart card is persisted. When the user logs out or logs in, everything is persisted, which is nice. This, you can think of it as if it's like a main function of the application. Essentially, there are 3 things the app should be able to do. First is get the persistent storage, then store these promises, and then pass some additional information to the extension. Because extension lives completely independently from the app. App doesn't start extension. System starts extension. So to get some information about what backend URL is, what is credentials to backend, stuff like that, application has to leave something, some bytes, and this configuration data allows you to pass some JSON, for example. All right, after you've done this, you can open System Profiler application and navigate to Smart Cards section, and you will be able to see all the registered signed identities there, and the usage for them will be that they can be used to perform code signing, which is what we want. Let's have a look how we get the persistent storage first. So you use this bundle ID to get the token driver configuration, which represents the extension. Then you create some stable identifier, which can be preserved between app restarts and system reboots. As an example, I think the serial number of the machine is a very good solution for this. And then, essentially, if it's the very first start of the app, you get the persistent storage. You create it for the first time, but for consequent restarts, you reuse the already existing persistent storage or token configuration. That's very easy. Then you assign the promises or keychain items into that persistent storage. Let's see how it's done. Obviously, you fetch certificates from backend, and for each certificate, you essentially have to create 2 things. One is the certificate, description of the certificate, and the other thing is description of the private key. So it's advisable for backend to serve certificates in their format, because there are other formats, and Apple API supports only there. So you fetch bytes for each cert, you convert them to 2 models, and you return them you set them to this token configuration. Let's explore these 3 dots. I don't want you to kind of dig into it mentally because they're a bunch of code, but if any one of you would like to implement this later, probably they can just refer to the slides. So you get the certificate from the server, you parse it, and you create sec certificate instance out of the bytes. And then you can actually explore that certificate using Apple APIs, like in this case, I get command name of the certificate. You create these 2 things, certificate and key descriptions. The important part here is that for the key, you need to expose the object ID, which extension will then pass to backend, which backend should be able to understand and refer to the corresponding private key. For simplicity, it's just for the simplicity of this talk, it's just SHA-256 of the DARE certificates. And then there's a bunch of more configuration for the key itself. It's all boring. I think the important part here is just we say that this key can be used to sign and nothing more. And that's the keychain items part. And again, after you do that, you get the smart card in the system profiler. That's how you can see the result. Let's move to the extension, where the interesting part happens. As I said, extension started by the system whenever code needs to be signed, automatically. You can't interfere into this process at all. It's heavily sandboxed. It means the extension doesn't have any access to file system, doesn't have any access to application environment, or cannot even query the other system processes that are currently running. But it can have access to network, obviously. Breakpoints were really hard for me. Apple engineer on forum says that they should work. I wasn't able to use them. So I used the old friend from 2003. And obviously you can use OS log for that purposes as well. And you can stream logs in real time using this command if you ever want, and you'll probably need. The template that Apple provides for the extension target creates a bunch of files, 2 files, token driver and the token itself. You don't have to look into them. You have to only mutate the token session file, which is where the whole logic lives. And the token session is essentially the delegate to it's main delegate, right, of the extension, where all the logic happens. You have to implement only 2 methods there. One method is system queries your extension. Hey, do you support this operation or not? And you just say that I don't support anything except code signing. Very easy. The second method you have to implement is when system tells the extension, please sign these bytes. And it provides you the identifier of the key, which, as I remind you, we happen to set to SHA-256 of the DARE certificate. It provides you the algorithm to use to create the code signature. And the code signature itself, again, is just a bunch of bytes. Very nice method, actually, right? I wish all Apple APIs were like this. Let's talk about algorithm, where the nice API ends. This is the algorithm. So you given this class. You close your eyes, you use your 2 fingers to touch the item on the table to understand what it is, right? You have to understand what algorithm you are asked to create the extension. Maybe I just not into security deep enough, but I find this very confusing. Why not property, right? And there are 50 plus different algorithms to query, right? So you have to query each one of them, probably, right? To understand what the hell operating system wants from you. That's not the case, luckily. Let's talk about what algorithm is. Algorithm is just 3 things combined into one object. It's a padding, which describes the schema of what the message from the OS, what format of the message from the operating system is. You don't really have to think about it. Usually it's PKC OS 1 version 1.5 in most cases, in all cases, actually. Then it's hashing. Very simple, how to hash the message. And then it's a Boolean flag whether message is already hashed or not. Again, not very clear. You have to consult ChatGPT version 5 to understand why message can be pre-hashed or not. So thing to remember, if the Swift symbol contains digest word, then it means message is pre-hashed, and if it contains message word, it means message not pre-hashed. As an example, this is one of the algorithms you need to support. And it's clear, right, how to extract these values, because backend will need exactly these 3 things to determine what algorithm to use on its side. Right. You have to support essentially only 4 algorithms, which is very nice, not all 50 plus. 2 of these are used by product sign tool to sign package files, and 2 of these are used by code sign tool to code sign the disk images and executables. Just 4 of these. So essentially, your extension starts to rattle a bit and smell because this ugly code you have to write inside the extension. You need to determine these 3 fields by actually querying, is this algorithm or it's not this algorithm? As soon as you determine these 3 fields, you can fetch the token configuration, which application handler left for extension, which may contain things like backend URL and credentials and everything else that you would like it to contain. And then you do a call to backend to create the signature. However, this method is not async, so the network call has to be synchronous. But we iOS developers, right, we are very good of converting URL session calls to synchronous. Just semaphore it and that's it. And you get back the result from backend. Now let's talk about this smoking person who digs the trenches and actually performs the code signing. It gets these things from extension. What bytes do I need to sign? Like what private key to use? I get it like by having SHA-256, as we already remember for the third time. Somehow it gets the private key by comparing SHA hashes, just for simplicity, because backend has all like private keys, right? It can have access to them. For simplicity, I just hard code the padding to be PKCS1. We determine algorithm. We see if it's pre-hashed. Then we just wrap the algorithm to pre-hashed. This is actually Python API without any third-party libraries. I find it very nice. And then we ask private key to sign the bytes. That's easy. I think the Go API should be very similar, or whatever language you choose for backend. They're all more or less the same. Even Swift API is similar. Some developer notes that I encountered during the development of this tooling. As I mentioned, you really have to start the app in Finder by double-clicking, or use the open tool to start the app in the GUI session, because if you don't do that, then the extension doesn't get registered inside some launch services in macOS. So for the very first time, you really need to start the app. As soon as you start the app, you can force kill it and use like CLI interface of the application executable to perform additional configuration of the extension. But for the first time, you have to start the app. Without that, there will be like nil pointer exception somewhere. Like it will be super weird, you know. Sometimes when you keep developing on the laptop, system profiler just stops showing the smart card, or like if it shows like it's empty or something like that. It means that system got confused. You created so many binaries for the single application version that macOS doesn't understand what's happening. Simply bump the version in the project settings, and that's it. That helps, resolves all these magic issues. You can actually use YubiKey as a smart card. That's very interesting. You can create the private key inside YubiKey. You don't need to write anything, and then YubiKey can do the code signing for you. So if it's on CI machine, you can insert the YubiKey to the CI machine, create private key on it, create like certificate signing request, upload it to Apple, get the actual cert back, and you will be like it will be impossible to extract the private key from in that case. And yeah, there's a good article about it on this QR code on the link. And you can do a similar thing using secure enclave. But in this scenario, you will need to code something in Swift and core foundation level. Smart cards that application exposes are created per user. So if you need different users to have access to the same remote sign-in operation, then you just need to start the app under the session. This is a very interesting thing. You would need to deterministically reference certificate. What I mean by that is like we all got used to set the sign identity to the string that looks like this. But when you renew the cert, there will be another certificate with the exactly same name. Even though you update the provisioning profile to refer the new certificate, code sign tool will still be sometimes confused that I see two certs with the same name and I pick random one and the whole thing doesn't work. It can be flaky on CI, for example. So instead of embedding this into the project settings or plists, you just embed SHA of the cert right inside the project settings like this, just remove spaces. And that makes everything very deterministic. Code sign tool will never get confused. It will always pick the correct certificate to perform the code signing. And audit, don't forget about audit. Whenever backend is asked to sign some bytes, it can log that to some audit database, right? And then it lets you answer the question, I see this executable around the internet. It is signed by us. But did I actually sign it? Or did someone stole my private key and signed it outside of my infrastructure? You can dump the hash. You can then query the audit. If you find the hash of the executable in your audit database, it means you signed it. It means, well, probably not great, but not terrible, right? But if you didn't sign it, it means that someone has a possession of the private key, which is bad. As a recap, I encourage you to implement this remote code signing tool thing. It's a very, very interesting project. I think if you have like a week and the whole administrative resource, like have access to all the machines, to the developer account, stuff like that, week will be enough to create a good MVP. And don't forget about audit, because whenever you talk about audit with your manager, it makes you smarter in their eye. And thank you very much for your attention today.